Good evening. I am Nobuyuki from Kobe University. So we are developing a microwave power transmission. So I would like to talk about our current and research. So we are developing a sandwich solar power satellite. We propose this type of the solar power satellite in 1995. So, and you can understand these. We have a pair of reflector, and this is a sandwich structure. On the one side, solar cell. On the opposite side, microwave power transmitter. So, and solar energy are reflected twice and concentrated on the solar cells. And electricity are generated by the solar cells and converted to the microwave to the ground. So John's idea is very similar. But anyway, we are you can understand the reflector is a very huge. Maybe it required to be a diameter of 5 kilometers, and transmit antenna must be over 1 kilometer. Too huge. So, but we have to reduce the weight of the sandwich structure. So maybe a structure must be flexible. So microwave transmitter antenna may be moving. So we need some control system to control the output phase. So we are developing a retro-directive antenna system. So we transmit power signal from the ground to the space antenna, and each antenna element receive a power signal, and to make a conjugate phase of the power signal. And microwave energy beam are transmitted from each antenna element. So it can realize to wavefront is so identical to the power signal. So it can realize to concentrate microwave power to the rectangular side. So even if space antenna is moving, so and this retro-directive system can compensate the distortion. So we are developing a real model of the phase array antenna with a retro-directive system. So you can see we fabricated 1, 2, 3, 4, 5, 9 panels. So and each antenna panel has an antenna for the power beaming and receiving a power signal. One panel. So and I want to show the vertical antenna pattern of the one panel. We measure the antenna pattern in vertical. So you can see the this picture shows a very narrow, very sharp antenna pattern. So in the vertical plane, and on the other hand, horizontal antenna pattern has a very broad pattern. So anyway, each antenna element concentrate in vertical, and in horizontal, it has a very broad antenna pattern. So it can control the microwave beam in a wide angle range. So I want to explain our demonstration. So this is a transmitter of the pulse signal. Transmitter for the pulse signal. And this is just a rover with a rectenna. So rectenna connected to the small motor. So if when the rectenna receives the microwave power, and it can drive this small rover by the electric motors. So and this is the 9 panels, transmitting panel. Each panel can radiate 20 watt. So in total, about 80 watt. And distance is about 30 meter. I'm sorry, just little dark. So this is the way I performed the demonstration in the Toronto in 2009, September. So, sorry, please. Yeah, thank you very much. Yeah, maybe you can see the transmitting antenna is here, and the rover is here. So this is a transmitting antenna for the pulse signal. So it can radiate pulse signal to the transmitting antenna. And you can see this is the patch antenna, so connect to the LED lamp. So pulse signal, so on the microwave is concentrated to the pilot signal transmitter. So it receives a microwave power to turn on LED lamp. Okay. So, and at the beginning, and I want to explain our measurement. So this is a pilot signal transmitter, and at first transmitting a pilot signal at a frequency of 1.225 gigahertz. So, and sorry, move to. So, and the microwave of 2.45 gigahertz is radiated to the pilot signal. So we measure along this line. So this picture shows our result. So pilot signal, pilot transmitter is here. So you can see main beam is same position of a pilot signal transmitter. So this is the first side lobe. And if move to the pilot signal, this point, so and the microwave power is a follow to the pilot signal. And yeah, we move to at the edge of the, yes. So and microwave follow the pilot signal. Yeah, can you understand? And next experiment. So and pilot signal radiate from here, and microwave is radiate, and we measure with together moving a power signal together with a measurement system. So this is I showed you. So this is when power signal is fixed, we can measure the antenna pattern. So, but if we move with a pulse signal together with the measurement microwave detector, so and it shows flat. So it means it indicates microwave. Our transmitting system follow perfectly follow to the pulse signal. And the next experiment, first radiate pulse signal and a microwave. So pulse signal approach to the small rover, and it can, it can move, drive by a microwave power. Okay, I will show you a bright now and dark. Can you see? Yeah, dark, bright. So I'm sorry, it is a very bright room. So pulse signal will move to the another position. Yeah, bright now and dark now. Can you see? Now, bright. And move together. Always bright. If I move with a pulse signal. Okay, next. Pulse signal is approaching to the rover, and the rover is moving, start to the moving. And if pulse signal is removed from the rover, so rover is stopped. Okay. You know? Anyway, okay, another picture. So, anyway, so but this is we designed to be a space antenna. So I told you a space antenna moving. So each antenna panel are moving like this. So we make just adjusting moving part antenna element. So, but it can work as a same as a flat. Always anyway. If we have a big distortion of the space antenna, so but a electronic system can compensate the distortion. Anyway, we thought we achieved the beam control system using electronic system. So next experiment. We brought our antenna to the Hawaii. So because Maui Island has a very tall volcano called by Haleakala, and Hawaii Big Island has two big mountain volcano. One of which is Mauna Loa. So we brought our transmitting antenna to Mauna Loa, and receiving antenna brought to the Haleakala. So we try to perform the experiment at the long distance microwave transmission experiment. So you can see this picture shows the top of the Haleakala, and you can see Mauna Kea, which is very famous with a telescope. And this mountain is Mauna Loa. We try to microwave from Mauna Loa to the Haleakala. So this is one panel. So and you can see Mount Haleakala here. So we set our 9 panel to a base plate of the space of the space between the antenna element. So it can realize a large aperture antenna. So the distance is about 100 meters. So it can realize aperture is just about 100 meters. So, but we try to the experiment. So, but this is the transmitter for the pulse signal, and this is the receiving antenna at Haleakala. So, but these data are pulse signal. So you can see very it has a very variation. So sometimes drop to the 20 dB, and so not constant. So but the phase is almost same. So, but 2.4 gigahertz concerning the 2.45 gigahertz. So you can see this is a 10 dB. So we have a very large variation in the receiving power. If microwave is attenuated 10 dB, so it means 1/10. So and it indicates it is impossible to power transmission between long distance from the between the high mountain. So we consider why the reason of this variation. So maybe reflection on the sea face, and maybe a cloud and atmosphere. So, but deviation is shown by a red mark. So, but it means when we have a very heavy rain, so we have a big distortion. So, but we don't have a rain during the experiment. So maybe instant microwave must be attenuated or scattered. Yeah. So, but in our experiment, the distance is 160 kilometers, very long distance. So, but in the case of the solar power satellite, the atmosphere is only 10 kilometers. Maybe we get no influence from the atmosphere. So, but we have to verify the influence from the atmosphere. So maybe you know this is a Japanese geostationary satellite called by ETS-8. So it has a very big pair of big antenna. So the diameter is about 15 meters. So very so it can radiate 2.5 gigahertz. So we try to receive a microwave 2.5 gigahertz from ETS-8. So this is a geostationary satellite. So and microwave pass through the ionosphere and atmosphere. So we can measure how is the large of variation. So this is the data from receiving power from ETS-8. You can see the horizontal axis is time, and this is the receiving power. So variation is very small, only 1.1 dB. So this case only 1.5 dB. So but ETS-8 has a very big antenna, so and it moving like this, so shaking. So and maybe this small variation maybe depend on the changing the shape of the transmitting antenna, and this timing is just a sunrise. So if we have any influence from the ionosphere, so oh sorry no maybe this mark shows the quantity of the cloud. So it shows 2 and 7. It not so cloudy. So this timing has a very a lot of cloud. So but cloud has disappeared. So but almost same receiving level. So it means no influence from the cloud and atmosphere. So and this is a sunrise. So this part is night, and this is morning. So usually electron density in the ionosphere increase like this. So if we have influence from the ionosphere, so and maybe receiving power must be changed. So but this data shows no change. So it means no influence from the ionosphere. So concerning the frequency, receiving frequency, so and little change. So it means Doppler shift. A geostationary orbit, so but a little moving like character of 8. So and the frequency suffers a little Doppler shift. And concerning the receiving phase, we received 2 antennas to compare the receiving phase. So you can see almost phase difference of the phase. So almost constant. So no depend on the cloud. And this point is the sunrise. And almost almost the same. Okay, anyway, this is the current observation. So, but we need more receiving data. So, and we want to confirm no influence from atmosphere and ionosphere. So, but it can realize solar power satellite. So, but I think it is very difficult to power transmission in the long distance on the ground. Yeah, that is my presentation. Thank you very much.